Hello. So we are back again with the lecture series on vector algebra. In the last class, if you recapitulate, we have talked about the first algebraic operation on vectors, that was vector addition. So today we will talk about multiplication, but at the onset, not about multiplication of two vectors, rather we will talk about today multiplication of a vector by a scalar. So what is that? If we have a scalar lambda and multiply it by a vector A, then the product lambda A is a vector collinear to the vector A. So when this means that if we multiply a vector by a scalar, we get another vector which is collinear to the original vector. And what about the length of the vector? The length of the vector mod lambda A, that is given by this equation over here, mod lambda multiplied with mod A. That means the new vector is a vector whose magnitude has been obtained by multiplying the magnitude of A by mod lambda. Why we need the mod sign? Because I have just told lambda is a scalar, it can be positive or negative. So we take the mod lambda. Say for example, if we multiplied the vector A by the scalar 2, then the magnitude or the length of the new vector would be twice A. So it will double up. We can see this in this figure. We have a vector A and 2A is a vector parallel to it or collinear to it, and the length is twice of the original vector. Another thing we should remember, that if we multiply the number, if the multiplier is something less than 1, then we will actually shorten the length of the vector. So if we had multiplied the vector A by half, then the length of the product vector will be halved, will be half A. So we see here we have a vector A, and now half A is a collinear vector with the length halved. Another thing, if we multiply with a negative number, what will happen? Say we multiply by minus half A. We remember that negative vectors are nothing but opposite vectors. So now minus half A is a vector collinear but directed in the opposite direction. So this is what we mean by, or what happens rather, when we multiply by a vector by a scalar. And what are the properties of this? The properties are as follows. First, we talk about the commutative law. So commutative law means that if we have a vector A and the scalar m, then ma is equal to an. So that means the order in which we multiply the scalar and the vector, that doesn't matter. Whichever order we multiply, we get the same answer. Next comes the associative law. So now suppose we have two scalars m and n, which are multiplied with the vector A, and we have a relationship like this. M multiplied with NA is equal to N multiplied with MA is equal to Mn multiplied first with the vector A. So basically, once again, in whichever order we multiply the scalars or the vectors, all the three, they can come in any order and in any pair, it does not matter. And next, the distributive laws. So we have two distributive laws basically. Suppose that we have two vectors A and B and two scalars m and n. Now the first one, m multiplied with a plus b is equal to ma plus mb. That means what we are doing on the left hand side, first we are adding the vectors and then multiplying with a scalar. That is same as if we had multiplied the vector by the scalars individually and then added them. And the second one, if we have two scalars and a vector, it also follows a similar relationship, that we add the vectors m plus n, multiply with a, and that is same again as if we had multiplied the scalars individually with the vector a and added up. Okay, so this completes the properties of multiplication by a scalar. Now next, before switching over to vector addition, we will talk about something else, that is components of a vector in a three-dimensional coordinate system. That means how we can represent the vector in terms of its components in a three-dimensional coordinate system. So here we have a three-dimensional coordinate system given by rectangular coordinates x, y, z. O is of course the origin. Now see in this figure that suppose A is the point with the coordinates 1, 0, 0. What does it mean? This obviously means that the length OA is 1. So now what can we tell about the vector OA? Vector OA, we can easily tell that this is then a unit vector in the x direction, because the direction is along the x-axis and its length is 1. And standard notation that a unit vector in the x direction is denoted by I. Similarly, if B stands for the point 0, 1, 0, then OB is again representing a unit length, and therefore now the vector OB will represent a unit vector in the y direction represented by G. And along the z direction, K stands for the unit vector, which is now here OC, since C represents the point 0, 0, 1. So once again, this OA, OB, OC, what do they represent? They represent the unit vectors along the x, y and z axis, and the standard notations are I cap, j cap and k cap, which we should remember and will be used in all the subsequent discussions. Now the next thing is, having understood this unit vectors, how can we represent a vector, or rather a position vector, in terms of this unit vectors, or rather in terms of the components in the x, y and z directions. So this we see in the next figure. So again we have a similar xyz coordinate system, and now we have the position vector OP or R, where P denotes the point x, y, z. So we know all that what does this P, x, y, z, the coordinates represent? This coordinates x, y, z represent that along the x-axis the point P is placed at a distance x, along the y-axis at a distance y, and along the z-axis at a distance z. So let us suppose that OQ, this stands for this distance x. So if we think of in the vector perspective, then OQ we can write as xi, because I stands for the unit vector in the x direction. Similarly, if this OS, this represents the length y, then as a vector it is yj, and the vector OR is zk. So having understood this, now let us see that how we can represent R in terms of this components. Now one more thing, let us first note that this, as we can see here, this parallelepiped, this P1P, this is parallel to the z-axis. So P1P is nothing but equal to zk, the vector P1P. Now if we start with the position vector OP, that means R, you see from this triangle OPP1, using the triangle law, this OP is equal to OP1 plus P1P. Now P1P, we have already told that P1P is ZK, and what is OP1? For this, getting this OP1, we now apply triangle law to this triangle OPQ. So OP is nothing but OQ plus QP. So OQ is XI, and QP, if we notice, this is parallel to OS. So QP is YJ. So then we get a very important and useful relation to be used in subsequent discussions, that the vector R is represented as Xi plus Yj plus Zk. So what we should remember then, that if vector r represents the position vector of a point P whose coordinates are x, y, z, then it can be represented as xi, yj and zk. So x, y, z are said to be the components of the vector r along the x, y, z directions. And from here we also get another important consequence, that the length of the vector r will be square root of x square plus y square plus z square. Why is it so? Once again, let's go back to the figure. If we look again to the triangle OPP1, and if you remember that this is a right angled triangle, right angled at this P1, so we see that r square will be given by OP1 square plus P1P square, which is Z. And what is OP1 square? This again, we see that this is again a right angled triangle, and now OP1 square is going to be x square plus y square. So r square comes as x square plus y square plus z square, and therefore the magnitude of the vector is root over x square plus y square plus z square. Once again, a very important relation which we come in many discussions. And next we talk about some more results using these components. So now suppose if we have two vectors a and b, where a is represented as a1i plus a2j plus a3k in the component form, that means a1, a2, a3 are the components of vector a, and b is represented as b1i plus b2j plus b3k, then see that we can write the sum of the vectors a and b, which we have learnt in our previous lecture. Now we can write the sum in the component form as a1 plus b1i plus a2 plus b2j plus a3 plus b3k. So that essentially means basically we are keeping the unit vector I and then adding the corresponding components. So a1 from the first vector and b1 from the second vector. So a1 plus b1i. Similarly, if we take of j, the components were a2 and b2 and so on. A very similar result follows for the difference also, a minus b. Again, we now subtract the components. So a1 minus b1i, a2 minus b2j plus a3 minus b3k. If we come for multiplication of a vector by a scalar, this is result number 4. This is also same. We do a component wise multiplication. So if we have lambda a multiplying the vector a by the scalar lambda, then it is going to be lambda a1i plus lambda a2j plus lambda a3k. Another point what we have put here in number 3, that these two vectors are equal means that the components should be equal. So that means we must have a1 equal to b1, a2 equal to b2 and a3 equal to b3. Okay, now one more thing, we have now looked into the component of a position vector, which was starting from the origin. But now if we have an arbitrary vector, say p1, p2, whose starting point is p1 with the coordinates x1, y1, z1, and the end point or terminal point is p2 whose coordinates are x2, y2, z2, how we will represent that? That is also very easy. So what we do now here, we draw the position vectors of p1 and p2 with respect to the origin. So we have taken this dotted lines OP1, which is now the position vector of the point P1, and here OP2. And now we have to apply basically the triangle law. Triangle law to this triangle OP1, P2. So what we see if we apply the triangle law, OP1 plus P1, P2, that will be equal to the third side OP2. So now from there what we can say, P1, P2 is equal to OP2 minus OP1. And what is OP2? From our previous knowledge, we can say that OP2 will be x2i plus y2j plus z2k, whereas OP1 will be x1i plus y1j plus z1k. So if we subtract using the result used in the shown in the previous slide, we get x2 minus x1i plus y2 minus y1j plus z2 minus z1k. So once again, a very important result to be remembered, that if we have a vector p1, p2, where p1 is having the coordinates x1, y1, z1 and p2 is having the coordinates x2, y2, z2, then we can represent the vector in the component form as x2 minus x1i plus y2 minus y1j plus z2 minus z1k. And using the previous formula for the length of the vector, so now the length of this vector p1, p2 will be root over x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. And I repeat that these will be very much useful results for our subsequent discussions as well as in your further course of study in engineering maths also. Okay, so with this we will close today's session, and in the next session we will take up actually multiplication of two vectors. Thank you and have a good day.